All right, let's jump right into this explainer and start peeling back the layers of a truly magnificent celestial object, Caldwell 22, or as it's more widely known, NGC 7662. If you've ever looked up at the night sky and found yourself wondering about the actual life cycle of stars, well, you are definitely in for a treat today. We're going to dive into some incredible data and research that breaks down exactly what is happening inside this glowing cosmic orb.
But first, we have to talk about the incredible irony of this object's nickname when you compare it to its actual blistering physical state. It's called the Blue Snowball Nebula. And sure, if you're looking through a small backyard telescope, it totally looks like a serene, frosty little blue snowball just suspended out there in the dark. But as we're going to see today, that calming blue glow is actually the signature of a 100,000-degree cosmic inferno. Literally, it is a dying star violently throwing off its outer layers in just a spectacular display.
So here's our roadmap for today. 1. Meet the blue snowball. 2. Anatomy of a nebula. 3. Mapping the expansion. 4. Chemical fingerprints. And 5. The central star engine.
Section 1. Meet the blue snowball, a cosmic gem in Andromeda.
Now captured by the Hubble Space Telescope in just stunning narrowband detail, this is the Blue Snowball Nebula. What we are looking at isn't just a single standard picture, but a composite. It's a blend of different gases glowing at completely different wavelengths. Hydrogen alpha, doubly ionized oxygen, nitrogen, and helium. So this isn't just some random blob. It's a highly structured, intensely complex cloud of gas.
Let's get our basic facts straight before we go deeper. Caldwell 22 is located in the Andromeda constellation. It was actually discovered way back in October of 1784 by the legendary astronomer William Herschel. Now, while some older baseline data placed it a bit closer to Earth, modern astronomical estimates place this magnificent object a staggering 5,730 light-years away. And regardless of the exact cosmic tape measure you use, it's categorized as a planetary nebula, which, by the way, despite the name, has absolutely nothing to do with planets. It's actually the remnant of a dying star.
Moving on to Section 2. Anatomy of a nebula, the cosmic onion.
Think of this nebula kind of like a nested Russian doll, or maybe an onion. Spectroscopic data reveals a really distinct triple shell structure. On the very outside, you have a massive, faint spherical halo just spreading out across the interstellar medium. Inside of that is a fainter outer shell, basically an envelope of gas. And then right smack in the middle is the bright inner shell, which is this highly dense, thick rim of material surrounding a hollow central cavity.
Now, space is three-dimensional, right? So we can't just look at it like a flat picture. To visualize this in 3D space, picture a prolate ellipsoid. Basically, imagine a giant rugby ball. The data shows that the main inner shell is shaped exactly like a rugby ball, and its major axis is tilted about 50 degrees toward our line of sight here on Earth. That tilt is exactly why the nebula looks a bit asymmetrical and has varying levels of brightness along its rim. And if we track the density of those gases from the center of the nebula outward, just look at how steep those lines get. The gas density drops off relatively smoothly as you move through that outer shell, but the second you hit that bright inner rim, the density spikes violently. We're talking about roughly 5,000 particles per cubic centimeter in that inner shell, which is incredibly dense for a nebula, before it plummets to near zero in the hollow central cavity.
Section 3. Mapping the expansion. Kinematics of the gas.
Okay, look at these numbers side by side. The kinematics, which is just a fancy way of saying the study of the motion of these gases, revealed two very distinct timelines. The inner shell has a kinematic age of about 700 years, and it's expanding outwards at a blistering 35 to 53 kilometers per second. But the outer shell is older, at roughly 1,050 years, and it's actually moving at 50 to 60 kilometers per second. Honestly, the most surprising takeaway here is that the outermost layer is outracing the inner shell. I mean, intuitively, you might think an explosion pushes everything out evenly, or that the inner stuff right near the engine would be faster. But what we're actually seeing is that as the dense gas of the outer shell diffuses into the near vacuum of space, it faces way less resistance. So it's allowed to accelerate and expand much faster than that denser, more restricted inner rim.
Section 4. Chemical fingerprints, decoding the elements.
So, the blue snowball isn't perfectly smooth. When we analyze its chemical composition, we find these incredible structural anomalies. It contains features called flyers, fast, low-ionization emission regions. which is a mouthful, but they are basically dense, super fast-moving bullets of gas just shooting out through the nebula. We also see emissions from molecular hydrogen trapped in these low-velocity knots. And most interestingly, modern data completely challenges what astronomers used to think about this nebula's overall chemical makeup.
See, older historical studies often classified the blue snowball as a carbon-rich nebula, but that was based on really limited visual spectrums. When researchers brought in data from the Infrared Space Observatory, or ISO, they were able to measure those spectral lines with much higher accuracy. And the conclusion? Carbon and oxygen are actually equally abundant. It is absolutely not strictly carbon-rich.
By plotting the carbon versus helium levels of NGC 7662 and then comparing them directly to our own Sun and the Orion Nebula, astrophysicists can map out a highly accurate chemical fingerprint. Cross-referencing these specific abundance ratios tells us exactly what kind of nuclear fusion was cooking inside that star before it died and shed all these layers.
Section 5. The Central Star Engine, the heart of the snowball.
100,000 Kelvin. The central star, sitting right there in the hollow cavity of this nebula, is boiling at an astonishing effective temperature of 100,000 Kelvin. Just to put that into perspective for a second, the surface of our Sun is about 5,800 Kelvin. This extreme heat emits fierce, intense ultraviolet radiation that ionizes the surrounding gases, making them glow and just completely shattering the whole snowball illusion.
This central engine is an absolute powerhouse. It's pumping out a luminosity roughly 5,250 times brighter than our own Sun. But what's really wild is that it's doing this from a core that only has about 60% of our Sun's mass. It's currently in what astronomers call the post-asymptotic giant branch phase. Basically, it has finished its red giant phase, violently expelled its outer layers, and is now on its way to cooling down into a white dwarf.
So how exactly does a dying star create this rugby ball triple shell shape? Well, it's explained by a really elegant physical process called the interacting stellar winds model. It happens in 3 steps. First, the dying red giant sheds its outer layers in a slow, dense wind. Second, the incredibly hot exposed core starts firing off a much faster, thinner wind. Finally, the fast wind catches up to the slow wind, slamming into it like a massive cosmic snowplow. This collision sweeps up the gas, carves out that central cavity, and compresses the material into the bright, dense inner shell we see today.
The overall consensus of the research we've been looking at points to one really clear conclusion. As the authors themselves point out, the detailed morphology is successfully reproduced by the interacting stellar winds model. The complex fluid dynamics of these colliding winds, combined with the sheer extreme heat of the central star, perfectly explain the anatomy, the speed, and the shape of the blue snowball.
I want to leave you with this final thought. We've seen today that planetary nebulae like Caldwell 22 are really just brief, explosive flashes in cosmic time, lasting only a few tens of thousands of years before they fade out into invisible white dwarfs. Now, our Sun is destined to go through this exact same process in about 5 billion years. It will shed its layers, create its own brilliant planetary nebula, and perhaps from some distant world look exactly like a glowing snowball in the dark. What does that mean for the ultimate transient fate of our own solar system? Thank you so much for exploring the blue snowball with me in this explainer today. Keep looking up and stay curious.